So, we're going to get through this. I do not see either class tomorrow. I see them both on Friday. So I may, due to the fact that you have 2 evenings before the next lesson, I may find one video from last year and ask that you watch it so we can catch up and reclaim some lost lessons. Okay? Please, let's just quickly revise. That if an object is not moving, it is in 3 states of equilibrium. The first is rotational. Thank you, Julian. Don't lock it. Cool. And many scenarios will be that you cannot solve part 2 before doing part 1. So I will say, as I did yesterday, we're going to do these questions in that order. Okay, so step 1, solve through rotational. Then remember, the trick is, if we turn over the page to the painter's scaffold, the trick is, if we analyse the point, the pivot at one of the unknown forces, it generates 0 torque because it's acting with 0 perpendicular distance. That then leaves one last force that we can solve for. Gentlemen, if you are using your devices, could I ask that you turn off your Wi-Fi? You can still use OneNote, you can still annotate on OneNote, but they're trying to troubleshoot why Mr. Murray is having so much trouble with this big white screen behind me. Okay, and they're thinking it might be lots of traffic for people on their laptops. So if you, I'm happy for you to annotate on OneNote, but just turn off Wi-Fi, please. Okay, so let's draw in all of the forces. Here is the trick that I said. By analysing the pivot at one of the forces, let's call that T1, let's call that T2. We've got weight 1, or weight of the person, and then weight of the plank. Okay? Now, if we try to solve using translational vertical, we have 2 unknowns. We know that T1 and T2 must be equal and opposite to 1700 newtons, but we don't know what they are each individually. Okay? So, let's consider, if we place the pivot point on the left-hand side, then T1 generates 0 torque about pivot point P. We can ignore it and focus solely on this guy is 5 meters along from the pivot, and it's providing a counterbalancing torque due to the moment of the person and the plank. And so we can solve for T2. So, step 1, let's get it written down over here. We always write the sum of all torque. Let me just go a little bit thinner than that, please. The sum of all torque equals 0. Torque equals RF sine theta. Clockwise moment equals anti-clockwise moment. Taking moment about P. Or taking torque about P. Okay? Then we get going. Now, remember, we haven't been given the distance to the centre of mass, but we know that it's L on 2. So you've been given 5. If you write down 2.5 without showing working, you risk losing marks. Okay, so you either do a little side mission that radius PL equals 5 on 2 equals 2.5. If you do that, then we're good. Okay. All right. So our clockwise moment, 1.5 by weight person plus 2.5 weight plank equals 5 T2. So the total clockwise moment produced by both person and plank is 3,550 Newton meters. Therefore, T2 equals that divided by that, 710 newtons upwards. Okay? Now that we've got our second force of 4, our third force known, we can find the fourth unknown. So now let's set sum of all forces Y equal to 0, which is weight person plus weight plank plus T1 plus T2 equals 0. Okay? Now, again, remember, I'm a rearrange first kind of guy, but let's throw everything in first. 0 equals negative 700 plus negative 1,000 plus T1 plus 710. All right? Do whatever you want. Solve whichever way you can. T1 equals 990. 990 newtons upwards. Okay? So those are our two answers. And you could check, oh, thank you. You could check, the total downward forces are 1700, and yes, the total upwards forces are 1700. The sum of all forces in the vertical are equal to 0. Now, your homework, or perhaps if we get 10 or 15 minutes at the end, I'd like you to analyze pivot at, let's go a lovely purple P. So, I just chose the left side. Half of the class could have analysed the moments about the right side. What you would need to do is just be careful. Things change. The person is now 3.5 metres away. Okay? And you would do exactly the same method. You would then, at this point, T2 creates 0 torque. We can solve for T1. You do all of the maths using rotational equilibrium. You would solve that T1 equals the 990 newtons upwards. And then you would use the sum of forces vertical. You would solve for T2 equaling 710. Okay? So I would like you to look at things from the other side. Do that either for homework or if we have 10, 15 minutes at the end. Also, you don't need my booklets or me or the Pearson chapter or the Giancoli or the past test. You can make your own. All right? The painter's scaffolding question, very, very regular type of question. If it is not 2 ropes that are suspending, it could be a trestle table where it is 2 supports at either end, which would produce an upwards reaction force. Don't write this because I'm about to delete it. It's a plank being suspended by 2 cables, or a trestle being supported by 2 supports. Okay? You can pick the length, the mass, where the person is. Depending on the variables that you pick, the reaction forces or the tensions will change. Let us consider the Christchurch swimmer. All right. Now, let's suppose I've got some values to throw at you now. Let's suppose that the center of mass is here and its weight of the board is 300 newtons. That's an N for newtons. The weight of the swimmer is the person is 500 newtons. Okay. I am going to analyze the pivot point. Now, if this was to topple, if those were the only forces or torques, it would rotate in a clockwise. And this point here, this part of the plank would be stationary. It would pivot about that point. So I'm going to analyze that pivot point there, P, in which case there would have to be a bolt screwed in behind, maybe by 0.2 meters. That's going to produce a downwards force. That is our counterclockwise moment to maintain rotational equilibrium. Okay, so it's on the other side. It's going to make a counterclockwise torque to balance. Okay, now, have we got all of the information? No, we don't. I'm just going to go over this in red. We know to the pivot to the end, for some strange reason, 0.4. The bolt, okay, so now we know that that's 0.2. Yes, what about from the pivot to the center of mass? What is that? What are we thinking? 0.6. If that's 0.4 and we've got to get to 1, yes, 0.6, I would agree. Okay, so occasionally you'll have to do a quick little arithmetic to find all of the R values. You might be given masses, so you have to do a side mission to find the weight force. If you include it in the equation and just call it mg, then you're fine. So, are we sick and tired yet of writing the following statement? Yes, we are. Right, get writing. Quick, you know exactly what I'm going to be writing here. Sum of all torque equals 0. Torque equals. Well, let's start with clockwise moment.
So you can abbreviate.
You can here. Abbreviations are allowed here. And we'll taking moments. What did I say before? Taking moments or taking torque about pivot P. Have I identified P in my diagram? Yes, I have. Brilliant. Let's get going. We have 0.6, weight of the beam was 300, plus he's 1.6 from the pivot and his weight's 500, and that's going to equal 0.2 force of the bolt. Okay, so our total moment clockwise is 980. Remember, you don't need to do that, but I like to just show you that that's the total moment that the torque of the bolt needs to produce. Force of the bolt equals 4,900 newtons. And from our diagram, if it's on the left side, to produce a counterclockwise, it has to be acting downwards. All right, so you can sort of look at the diagram and go, yes, it has to act down. If it acted up, then our board's going to be spinning around like some kind of glitching game, you know. So Bethesda, yes, Fallout 76. Thank you. Downwards. Right. Now, that's actually quite a large force. If you have a look at why that is. These two forces are acting a really, really long distance away from the pivot, so they produce a really, really large torque. The bolt needs to counter that. But Robert Lee, the bolt doesn't have a very large leverage. Its lever arm is only 20 centimeters. And so if R goes down, F must increase to produce the required 980 newton meters. Obviously, if this concrete block was 2 meters long and you placed the bolt down, well, if we increased our leverage by 10, our required force would go down by 10. So a 2 meter long concrete slab would make the force only 490. That also has another interesting effect. If those were the only three forces on the board, it would be accelerating down at 9.8. Or, no, it wouldn't. It'd be accelerating faster. But it's not, because there's an upwards force, a reaction force at the pivot. Have a think. This is kind of like some kind of weird nutcracker. You could put a nut there, and you could crack it using the leverage of the torque produced by the board and the diver. And unfortunately, it's also going to be quite large. So again, step 2. We can now solve that equals 0, which is force of the bolt, reaction force of the block, weight of the board, weight of the person. Again, I'm a rearranging kind of guy, but let's just again equate it to 0. We've got negative, where was it, 4,900 plus negative 300 plus negative 500 plus FR. They're all negatives. Throw them on the other side. They all become positives. FR equals 5,700 newtons upwards. Okay? So, homework. Oof. Here's the thing. Same kind of deal. If you've got a flat horizontal board on a flat horizontal surface and you said, let's just let the thing fall into the water, then yes, the natural pivot point would be there. But a little trick is we could do exactly the same. We could analyse the pivot here like a nutcracker. If you put the pivot there, then same thing as the scaffolder. You find the other unknown force first. Okay, so for homework, or the end of the class, if you put the pivot here, you would find FR to produce the counterclockwise moment, and its force would end up being 5,900. Then you would use translational vertical. You would then find that this must be minus 4,900. Okay? So there may be questions where you have options. Half the class might go, I'm going to analyse the pivot point here. The other class Or the other half will analyse the pivot on the other side. There's no right way to it. Sometimes there's only one pivot, and we'll look as the questions get a little bit trickier. There might only be one area. You have to analyse it there first. Yes?
If you move the pivot to the left side, would the FR also move with it?
No. So if you take the pivot about the bolt, so for your homework, if you did that, then the force is still acting, but it's generating zero torque about that point. So we can ignore it.
Yeah.
When we sum the rotationals, it's that must equal that plus that. That must equal that plus that. Okay? And you get exactly the same answer. Okay? Now, underneath, could you please just draw a line? Hopefully you've got room. We're going to do some postcard work here. Damn it, it was 0.0828. Yes, cool. Here I have a system which is in equilibrium. It's not spinning around, it's not flying up and down, left or right. It's in equilibrium. What I've got is a 1 meter long piece of wood. Its centre of mass acts midway because it is of uniform density, and it is 0.0828 kilograms. I've got a pivot point at the 25 centimetre mark. I've got 500 grams at the 5 centimetre mark, and wouldn't you know it, it's not. There's 500 grams at the other end, and I have to apply a force upwards to maintain rotational equilibrium. So on its own, it's going to fall. What I can now do is put it on a surface. If I place it on the scale will produce an upwards reaction force. Alright? And I want you to calculate what that upwards force must be. And then if you divide by 9.8, it will give you the mass, the imaginary mass that's sitting here. Because remember, it's feeling a downwards force, it's providing a reaction force. So, I'm going to quickly sketch this, and you are also going to quickly sketch this scenario, okay? Here's our pivot point, P, all right? And it's at the 25 mark, so 0.25. We have a weight force, or a mass, of 0.0828, okay? 20 centimetres behind, we have a 0.5 kilogram mass. Okay. Then I'm just going to quickly sketch above. To get to the 500, I'm at 97, take 25, I'm at 72. 72 centimetres, or 0.72. Okay, so 0.72. I have a downwards force produced by a 0.5 kg. Now, as we said, if those are the only three forces acting, weight of the ruler, mass at 72, and a counterbalancing over here, then yes, that's not in equilibrium. And you could show that the clockwise moment does not equal the counterclockwise moment. So, we need to determine FR. Alright? So now look what's happening. We have four forces, two of them producing from the diagram, a clockwise moment. Sorry, I've gone the wrong way. Two of them producing a clockwise moment, the other two anti-clockwise. Okay? So, get solving. You're going to solve for FR. How many newtons must the scales be pushing up? You then divide that by 9.8. It'll give you a mass. Then I want you, once you've got your mass, please come up and have a look at the reading on the scales and see if your reading is correct. Okay? Cool beans. So you guys get going. I will join you in just a moment. So, we've got 0.25. Don't forget to times by 9. We could cancel out the 9.8s and just leave it, but no. Let's get values here. Was that 7.2? It is 7.2, sorry. It's 0.72. That, I'm going to go off the screen here, but that's okay. That equals 0.2 okay? Now this here is 4.9 plus 0.72 FR. Now I'm just going to quickly calculate the total clockwise moment, and I'll write it down. 0828 times 9.8 plus so our total clockwise moment is 3.731, right? Now this is the cantilever example, right? We need to oppose that. If that's 3.73 clockwise, I need 3.73 counterclockwise. The cantilever is already providing, so this little buddy here is already providing 4.9. Oh, hang on, is that right? 0.49, my bad, I'm bad at maths. Whatever, yes, even much better, not whatever, thank you gentlemen. 0.98, that's much better. The counter lever is providing 0.98. So the reaction force need only provide that, take that. The remaining 2.7 will be provided by the reaction force. So FR equals 3.731. Has anyone got a number? Don't shout it out. Come and have a look, Mahoney. And delight as your number equals the number on the scales. Oh, the kid in the other class, he ran to the scales. He wanted to be the first.
Oh, you're joking. You're kidding.
What?
I'm off by 3 grams.
Crap. That's
2.4 grams actually.
That's less than 1%. I'm happy with that. And let's just check, providing if I was to put that exactly at 9.7, maybe, calm down. For God's sake. There we go. Tear it.
No.
Damn it, did it get worse?
Oh no, I've got slightly better.
Okay, and this one we're assuming it's exactly at 0.5. There is no friction.
I'm off by 1.8 grams.
Would somebody like to give me the reaction force on the screen? What did they work it out to be? Anybody? Anybody? Bueller? Bueller? 3.92? 3.82?
Yeah, well, according to that, 3.80.
3.80.
Yeah, 3.8.
I'll just do it myself. It's just 3.82.
Yep.
1. Then if we divide that by 9.8,
Then that's 0.390.
0.390 kilograms. That is what the scale should read. Oh my gosh. It reads 0.390.9. It's 1 gram above. 1 gram out of 390, that's like 0.25% off. So I'm happy with that. In our next lesson, I'm going to get a different ruler. I'll have a cantilever. I'll give you the reading, and I'd like you to find me the mass of the ruler, knowing that its mass acts midway along its length. So that'll be a fun little activity. Hopefully. All of our rulers are identical, but maybe I'll find... Oh, we've got a plastic one. I'll see if I've got a different ruler, and then we might be able to find the unknown mass by solving rotational stuff. Okay. Last question. Over the page. Gentlemen, if we have been designed poorly. If we have evolved pretty well, but also poorly. our bicep, big old muscle here, attached to our humerus, it fuses in with a tendon into our forearm. And when we want to flexor our blah, 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 it pulls, with a tendon, it pulls your forearm upwards. All right, and then you've got your tricep, which does the opposite. This tendon is only about 5 centimeters away from the elbow, which is the pivot point. Okay, so if I've got a lump of meat and I hold something that's at the end of my arm, my tendon is actually applying an upwards force. And as I said, because it's such a small distance, the force is actually much, much larger. But tendons are fairly strong, and our bicep muscle is actually quite a powerful muscle. Because it's been designed poorly, it has to be very, very strong in order for us to lift things, because the tendon fuses in close to the pivot. So let's add in this diagram. Our pivot is going to be here. Okay? Our center of mass of our forearm. Now I'm going to give you a 29.6 Newton forearm. For some reason I poorly multiplied 3 by 9.8. That is not 3 by 9.8. So our mass of our arm is a little bit more than 3. And then we have our 1 kilo or 9.8 Newton weight at the end. Next, our arm is not uniform density nor uniform volume. And so we can't just say the center of mass is midway. Obviously you've got more flesh closer to your elbow, less flesh further from your elbow. So I'm going to tell you, let's say that our center of mass of our forearm acts 15 centimeters, okay? And then our bicep tendon is going to be the force there. So again, we've got two clockwise torques and then a counterclockwise produced by the bicep. Okay, so blah, 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 blah. Sum of torque equals 0. Torque equals RF sine theta. Clockwise moment equals anti-clockwise moment. And then taking pivot about P, which we have identified. And we get going. 1.5 by 29.6 plus 0.35 by 9.8 equals 0.05 force bicep tendon. And then force of bicep equals 0.15, 29.6 plus 0.35, 9.8. Now, I haven't evaluated that. It's not much. You don't have much mass and it's not far from the elbow. But when we divide by the radius, which is tiny, we get a massive number. We get 157 newtons upwards. Okay? Now again, a massive value up for two quite small values. If you look at the two small values down and a massive value up, there is another force here on the elbow. What do you think is providing the force and which direction is it acting? I'll say it, I don't want to give you the answer. What's providing the force? Huh?
Are we talking about the muscles providing the force?
No, so if I just said this is our object, it's relative, yep. We've got an up and two downs. There has to be another down. Where do you think it is? At the pivot. It's actually going to be the humerus, your big bone, is actually pushing down on the elbow. Okay?
Oh, weight force?
Well, no, not weight force, just some kind of compression force in the bone pushing down. And very quick maths, it's going to be that, take that, take that. I'm bad at maths. 110 odd. It's going to be about 110 newtons-ish. You can solve it, but we're running out of time. The last little tricky thing that I'd want to put to you is, when we were at 90 degrees, everything was at 90 degrees. Sine of 90 was 1, all right? So it was just RF, RF, RF. If I was to take my forearm And decentric flexor, it's to 45 degree. Anyone doing human body PE studies? Eccentric flexor, concentric I don't know. 45 degree below horizontal. What would happen? Would anything change? Let's just quickly draw what I've asked. Here is my pivot. Here is the line of action about which my bicep acts, FB. My forearm acts, what did I call it? I didn't call it anything. Oh boy. F forearm. And then our F of our mass. So if I was to drop this by 45, I'm not going to draw, you know that it's 45. Oh dear, I've gone too far. F bicep. Then this angle up here becomes 45. This angle becomes 135. And this angle becomes 135. Okay? Now, this is a tricky question, and it may have been in a past test. I'd love it to appear in an exam, because you think that maybe the force goes up, because now the angle's decreased. But the same decrease in that angle is going to be the decrease in torque of this angle. We'll see that it cancels out. Let's have a quick look. If I was now to consider R forearm, weight forearm, sine 135. That's the torque produced by our arm. Plus R mass, weight mass, sine 135. That would then equal, I'm just going to move this out of the way. That would then equal R bicep, force bicep, sine 45. Okay? If we rearrange for force bicep, it's going to be sine 135. I'm going to put that out the front. It is a common factor to both RF, WF plus R mass, W mass over R bicep sine 45. What we have here are the supplementary angle, which will be the same. Basically, here's our unit circle. Boom, 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 and boom. We're just on either sides of the unit circle. Those will cancel. Sine of 135 is the same value as sine 45. And so it does not matter the angle of your forearm. The biceps tendon will maintain, providing there's no acceleration, of course. If we held the object at 45 below the horizontal, it would still give you a force of 157 newtons. Isn't that lovely? Okay. So a nice tricky question, similar to the prac that we did with this the circular motion. A lot of students would comment on the effect of one torque direction without realizing that the same effect occurs on the counter torque. And they are going to be affected by the same sine of the angle. Okay? As we get closer to the test, I will show you sort of the way you could answer this if it was an explanation question. If the question said, state the effect of increasing the mass in the hand, then I would come back to the force of the bicep is proportional to the weight of the mass. All other constants, all other variables remaining constant, as m goes up, the force of the bicep will also go up. Not proportionally, because it's stuck in the brackets, but anyway. Guys, please go back and do your homeworky questions. You have that for the cantilever and this for the scaffolder, and also a try yourself. You might wish to set some values up, and between yourself and your partner, work the questions, and hopefully you agree that you get the same answer. So, last 10 minutes. Please get those questions done. Analyze things from the other pivot. You will get exactly the same values. And that lesson went quite nicely. 35 minutes.